we talked about, at the end of our Calculus 1 course, volumes of surface of revolution. Remember we had those two methods, disk method, shell method. No? Well, same idea, except we're not doing volume. We're going to do surface area. So this is also on the handout there. If you go to turn over there, numbered page 31. I've got this, so if you don't want to draw these all out, I'll attempt to, but 31. Yeah. You got page 31, right? Yeah. Okay. All right. So yeah, what I've done there is we do the same thing that we did with the volumes. We take a curve. In this case, we're going to do y equals f of x from A to B. And we're going to rotate that area, if you will. Rotate that about an axis, in this case the x-axis. And that's going to generate, what do you want to call it? Lampshade? Sort of a lampshade. Better picture. I did better on that. Yeah, this one. You don't really see that. So, all right. So we get this shape here. So yeah, previously, you won't have to find these, but previously we found the volumes of those. What's the volume of that? Well, that would probably be our disk method, but that's not what we're doing here. The question is going to become, can I figure out the surface area? And it doesn't count, it's just the body. It doesn't count, because the two ends are circles. I mean, if you wanted to, you could get the area of those two circles, just tack it on. But we're talking about the area here of this surface, the body of the lampshade. Okay. Well, turns out the way we do that is we use, it's not a cone form, it's the frustum of a cone, which, if you've got a cone here.
Say the what?
Frustum. It's down there on the bottom of the page.
Okay.
Yeah, so there's a cone. The frustum of a cone is just, it's the top part cut off of a cone, basically what it means. So we're going to get rid of that top cone area and the frustum of a cone. So on a frustum of a cone, what you've got is two radii, a radius down here for the bottom, radius 2 they call it, and then the top radius 1. But then you also need this slant height, L. We're used to doing the height of the thing, but for this frustum, for the surface area, we need that slant height. Call it L. Well, I won't actually compute it, but, and then I flip over there, page 32. Really, the orientation of these frustums is going to be kind of sideways, and so we get more like this sort of looking thing. So you got your radius 2, radius 1 is in here, and then your slant height is there. Well, turns out the surface area of a frustum of a cone is pi times R1 plus R2 times slant height. Well, where does that come into R's? Well, yeah, what we wind up having here are, I divvied it up into 3. Should I try? Guess I'll try that over here. So if I divvy it up into 3, and then well, that's a y equals f of x from A to B. Talking about x1, x2, x3. zeros back here. If I rotate those then, well, and then I take these straight segments there, what I wind up with is, yeah, should even try that. Frustrums, 3 frustrums. That's not too bad. I'll do it. That looks like a space things the astronauts come back on. Not the space shuttle. That's the only way to think about it. The landing capsule. Yeah. It's capsule. Yeah, there you go. Landing capsule. That's what it looked like to me. I don't know why I thought that. But anyway, that is, and this is really the first lampshade ever drawn, but these 3 frustrums approximate the area, this shape here, but they're frustrums, and so I've got this formula I can apply and come up with the surface area of each one of those. So the surface area of each one of those would be, like for S1 here, it would be pi times, radius 1 plus radius 2 times the slant height. Okay, so S1 is pi. All right, what is radius 1? Well, radius 1's that, which would be, actually mine, what did I do? Oh, I have a different function.
You didn't draw the top there. The top one's just not drawn at the left side, it's not curving down.
Yeah. Anyway, this first radius is, it's just a function height at x0, isn't it? Then the second radius would be, the radius back here is just that that height there, which is, that's where I messed up. It should have gone down instead of up. But anyway, now the slant height. This is the beauty of it. The slant height is just that arc length. Call it L1. All right. So what I wind up with here, and we're going to use the the arc length formula on that. Yeah, arc length is the square root of the 1 plus the derivative squared at interval. Yeah. Now, as we get closer and closer together, what we can do is basically just combine those when they get so indistinguishable. I mean that those two function values, one and the same. And so we're just gonna. That's what they do for simplification purposes. Make that into a 2. So S1 is approximately equal to then pi times, and like I said, we're going to call those equal to f of x sub I star. And then from our arc length discussion, arc length is 1 plus the derivative squared dx for previous work. So that's 1 over. We put them both together, put all 3 of them together, then we've got the sum of the total surface area. So that gives us the surface area of 1. We add all 3 of them up. I equals 1 to 3, 2 f of x of I star. Square root of 1 plus f prime of x I star. Put that there. Squared delta x. Well, to get better, you need more, 50, 100. To get it equal, you need to run limit as n goes to infinity, I equals 1 to n. So do n, make n more, but to get it equal, we need to go to infinity. Long story short, here's what we get.
Where'd the pi go? Is this supposed to be
Yeah,
down?
it's
Did it
supposed to
go
be
to
pi.
this?
I forgot the pi. Right here. There's a pi there, just forgot it. Well, that's just the integral. The integral of 2 pi f of x times the square root of 1 plus f prime of x squared dx. So what does that give us? Surface area, the area of the surface obtained by rotating. So what did we rotate? We rotated y equals f of x about the x-axis. So here's another formula for your formula card, right? So it's obtained by rotating y equals f of x about the x-axis. Because remember, things changed when we rotated about different axes and different functions. This is y equals f of x about the x-axis, and x is in between a and b. That's the surface area form. And I don't think it's too hard. Oh, yeah, okay. I don't think it's too hard to imagine then. If I rotated a function about the y-axis, we would probably want what? X equal function y about the y-axis. And it would change to 2 pi f of y plus times the square root of 1 plus f prime of y squared dy. I don't know that I gave you any of those, but just FYI, okay? All right, so how about we try a couple of those? See what we run into with these. All right, so find the area of the surface. Obtained by rotating. Y equals the square root of 4 minus x squared from -1 to +1x about the x-axis. And it's kind of interesting to think about, you know, what we're actually finding here, what surface area we're finding. What is this? Anybody recognize that? Semicircle? Semicircle. Yeah. All right, so we've got a semicircle, and its radius, is that what you said?
Yeah.
Sure, good.
Yeah.
All right, what's the radius?
4, 2.
2. Radius 2. All right, so we've got radius 2 semicircle.
So a sphere.
Well, we're only going from
Oh,
-1 to +1.
so a disk.
So we're rotating that about the x-axis, and so yeah, we're finding
A donut.
it's sort of a well,
Wheel
it's a
cheese.
solid, kind of a wheel. It's a wheel shape, isn't it?
Wheel of cheese.
Wheel of
Oh,
cheese, yeah.
Sorry.
Yeah. We're finding that surface area, you know, the tire, just the outer part of the tire, because it doesn't, like I said, it doesn't count the end caps, the end circular end. So it's kind of interesting, kind of a tire surface area. Anyway, let's see what this is. Well, we got the formula. Rotate about the x-axis, all that good stuff. So, surface area would be the integral -1 to 1, 2 pi f of x, so that's f of x, square root of 4 minus x squared, times the square root of 1 plus the derivative squared. All right, so what do we got for the derivative? Well, that's 4 minus x squared to the 1/2. So the derivative is going to be 1/2 4 minus x squared to the -1/2. But then let's not forget the other part of that, which is, what's the other part?
Minus 2x.
Minus 2x, chain rule. And let's choose to write that, the 2's cancel. Let's choose to write that as x over the square root of 4 minus x squared. That'll help us a little bit as far as simplifying this. Okay with that? Negative x. Negative didn't cancel out. So I've got a negative x, and then flip that over and make it the square root on the bottom. Okay? All right, so that's what I square in here. So I want that, and I want it squared. Because it's 1 plus the derivative squared. So I need that squared. Okay. So that looks kind of interesting there.
There's 3 square roots.
Huh?
There's 3 square roots there.
There's
Square-
yeah, there's lots going on, yes. -1 to 1, 2 pi, square root of 4 minus x squared. We'll leave all that for now. All right, then this, well, this actually works out not too bad, right? This is a fraction. I can square the top, which is be x squared. Square the bottom. What happens there?
Just cancel that.
Yeah, the square root and the square cancel, so it'll just be, on the bottom, just be 4 minus x squared. Of course, it's all in the square root there, but that part, sort of. Okay. Now, what do we do from here? A couple ways you could look at it, I suppose. Yeah, let's go ahead and do it this way. Let's go ahead and make this one fraction, combine, add these two together. So what would I need? Common denominator? Which common denominator would be 4 minus x squared. And so make one be 4 minus x squared over 4 minus x squared. Plus the x squared over 4 minus x squared. So this, without having to rewrite it all, so it'd be 2 pi times the square root of 4 minus x squared. So what does that make this then? Well, it'd be 4 minus x squared plus x squared over 4 minus x squared. That works out pretty good, doesn't it? Yeah, this is going to be 4 over 4 minus x squared. Well, not hard to see there that I can split that up now. Square root of 4 over the square root of 4 minus x squared. I mean, I can split up. I can't split up adding and subtracting square roots, but I can split up dividing. You know, if I've got square root of a over b, I can say that's the square root of a over square root of b. As long as I'm dealing with positive numbers, I guess, but which I am. So anyway, this is going to work out pretty nicely too, isn't it? Basically, I'll wind up with 2 pi times 2 dx, or 4 pi dx. It's my integral, what I have to integrate. Yeah, square root of 4 minus x squared just cancel out. That's just 4 pi x, isn't it? So it looks so intimidating, but you know, we did everything, comes out pretty nice. And then we go from -1 to 1, so you got 4 pi times 1 minus 4 pi times -1. What do you got? 8 pi? 8 pi.
I couldn't have
So,
guessed that.
huh?
Couldn't have guessed it.
Probably wouldn't have guessed that, no. Probably would not have guessed that, but it worked out pretty nicely for various reasons. I mean,
More than it-
those canceling out, it wouldn't quite work so nice. I mean, if you think about it, okay, so think about this. I mean, if we were doing the arc length, we wouldn't have this stuff. So we would just have 2 over that, but that's also not that bad, right? That's not that bad. 2 over, isn't that just, that's a sine inverse, isn't it?
Yeah.
Yeah. So if we just had that, you know, it's a sine inverse, that's the arc length. So anyway, let's try one more. You got one more plan.
Yeah.
All right, so find the area of the surface. Obtained by rotating. Y equals x cubed over 9. X is between 0 and 1, about the x-axis. All right, so let's see what good stuff we run into here. So the surface area of y equals f of x rotated about the x-axis is the integral from a to b. Since I erased it, I'll write it up here again. 2 pi f of x times the square root of 1 plus f prime of x squared x. That's our formula. So what does that work out to be? 0 to 1, a to b, 2 pi, what's my f of x? X cubed over 9. Times the square root of 1 plus the derivative squared. So what's my derivative here? We got 1/9 x cubed basically there. So it'd be 1/9 times 3x squared, which is 1/3 x. 1/3 x squared? Is that the derivative?
That's what I got.
Okay. All right. So it'd be 1/3 x squared squared. Don't forget to square it. It's actually important. It'll make things work out so much nicer here. Okay. So let's rewrite this. Let's make it 0 to 1, 2 pi over 9. Kind of group those two together. 2 pi and 9. Times x cubed. And this will be the square root of 1 plus, what's that, 1/9 x to the 4th? All right. Now, what do we do? Well, this one works out so very nicely because of that and that. What do you see as far as doing the integration here? What technique?
U-Substitution.
It's U-Substitution, yeah. But U-Substitution will work because of the way the functions worked out. U-Substitution. Use the stuff under the square root, 1 plus 1/9 x to the 4th, which makes du, the derivative of that, be 4/9 x cubed dx, which means dx would be divide by 4/9, so du over 4/9 x cubed is my dx. Yeah, that's going to work out really, really nicely. Two pi over 9 x cubed square root of u, because u was the stuff of the square root there, and then du over 4/9 x cubed. This is going to work out very nicely because then the x cubes will go out. Now, divide by 4/9 means times 9/4, so this will be 2 pi over 9 times 9/4 square root of u du. That's doable. I think the 9's cancel and 2 goes into 4, so we have pi over 2, just pi over 2 here. Then I'm just doing the square root of u antiderivative, which is u to the 1/2, so you add 1, but u to the 3/2, and then multiply by the reciprocal 2/3. We can do, once we get back to x equals 0, x equals 1. So just wind up with pi over 3, and then u is, what was u? 1 plus 1/9 x to the 4th. Root to the 3/2. And that's from 0 to 1. Okay, so let's just leave pi over 3 out here. So it's pi over 3, plug in 1, 1 to the 4th is 1, so it'd be 1 plus 1/9 to the 3/2 minus, plug in the 0, that's 1 plus 0, so that's 1 to the 3/2. Again, we got a minus 1. What's 1 plus 1/9? 10/9? So we have 10/9 to the 3/2 minus 1. So that's a pretty good answer. But, again, they will probably simplify that. If you got that, that's okay. But what about this 10/9 to the 3/2? Well, of course, that we could do the top 10 to the 3/2 divided by 9 to the 3/2, top and bottom by 3/2. And actually, 9 to the 3/2 is pretty nice. What is 9 to the 3/2? Remember?
27. Or not 27.
27, yeah.
Oh, okay.
It's 27 because denominator 2 means square root. So you got square root of 3, square root of 9, which is 3. And then cube that. So yeah, the bottom is 27. And then there's that 10 to the 3. I think we had that earlier. 10 to the 3/2. Well, it's basically the square root of 10 cubed. Square root of 1,000. 2,000 is 100 times 10. So that's 10 square root of 10. Probably how they would write that. I don't see anything else. Whether it be that one's just about as good as that one. But anyway, with me there? Is that okay?